We are going to design a mat foundation for this tower. In ASMTower software, the design of the mat foundations depends on the analysis of finite elements. It's not just spreadsheets with simple calculations. ASMTower uses shell elements to model the mat with iterative analysis to solve the problem of contact with the mat on the soil. After the analysis is completed, a detailed report is issued. The report includes some images that show the dimensions of the foundations and show the pressure on the soil from the foundation and show the maximum bending moment of bending in the mat. The use of finite element analysis is more accurate than manual methods. Manual methods assume that the foundation is infinitely rigid, but the finite element can perform analysis of a rigid or flexible foundation. From the Foundation group, Lattice Tower group, open the Mat Dialog Foundation box. You can add multiple foundations with different dimensions and soil properties in the same tower file. Enter a foundation name. This name can be used once and should not be repeated with any other mat foundation. Select the Material Properties tab. Enter the allowable net bearing capacity. You can get it from the soil report. Most of the soil reports show the allowable soil bearing strength, but TIA-222-G and H need to calculate the pressure on the soil due to the factored load and compare it with a reduced soil nominal strength. In the soil report, the allowable bearing strength is calculated by dividing the nominal soil strength with a suitable safety factor. To obtain the nominal strength of the soil again, ASMTower multiplies the allowed soil bearing strength by this factor of safety. If the soil report shows the safety factor used in its calculation, enter its value here. If the safety factor used in the soil report is unknown, TIA-222-G and H lets you assume that it is equal to 2.0. The lowest value is the most conservative value. Assume the internal soil angle of friction is equal to 30 degrees. Set the soil density equal to 1600 kg per cubic meter. Set the density of concrete is equal to 2400 kg per cubic meter. Set the concrete compressive strength F-C equal to 21 megapascal. This value is based on a cylindrical test. Set the yield strength of the reinforcement bars equal to 420 megapascal. Set the yielding strength of the stirrup reinforcement equal to 420 megapascal. Select the Geometry tab. You can manually enter the forces applied to the foundation from the tower. Therefore, you can design the foundation for the reaction of the tower analyzed in other software. In this example, the reaction forces are automatically obtained from the tower we just analyzed. Select this option to allow the ASMTower to automatically get the reaction from the tower analysis. Select Leg Force Tap. You see that the reaction table is filled with tower reaction. Note, these reactions will not be removed if you uncheck the automatic reaction option again. But if you leave this option checked, these reactions will be updated each time you perform an analysis of the tower. Let's assume the initial dimension of the foundation. Suppose that the foundation is square and that the length is equal to width and is equal to 5 meters. The depth of the foundation is the distance from the bottom of the foundation mat to the ground surface. Set it equal to 2 meters. Set the thickness of the mat foundation equal to 0.5 meter. The foundation is now drawn to the right of the dialog. I noticed that the width of the face of the tower was closed to 6 meters after we chose the automatic reaction. Set the width of the foundation column or pier equal to 0.5 meters. This width should be large enough to avoid a clash between the anchor heads and the column reinforcements. It's common practice to set the column width at 0.15 meters larger than the width of the tower base plate. The column is drawn in the lower image on the right side. Set the height of the column above the ground equal to 0.3 meter. In the foundation figure, you see that the 4 columns are outside the foundation. This is because the face of the tower is equal to 6 meters, and we set the width of the foundation to 5 meters. The design of mat foundation consists of 3 parts. First part is the stability evaluation, which aims at removing the possibility of failure of foundation by overturning, sliding. The second part is to check the bearing capacity of the soil. Soil pressure is calculated in 2 methods, one of which is approximate, assuming that the mat foundation is rigid and is used to determine the initial dimensions of the foundations, and the other method is accurate using finite element analysis and used in the final calculations in the report. The third part is the structural design of concrete foundation, comprising of the design of columns and the design of base slab. In the design of the mat foundation, ASMTower make 9 checks to evaluate the foundation. Overturning check. Soil check using approximate stress on soil using manual methods. Sliding check. Punching check. Check on the vertical reinforcement in the column. Check on the stirrup reinforcement in the column. Soil check using stress on soil from the finite element analysis. Check on the bottom reinforcement in the mat. Check on the top reinforcement in the mat. At the top right, you see 9 small grey squares. Each square represents one of the 9 checks. The colour of the square will change according to the usage ratio. See the meaning of colours in the lower right corner of the dialog box. Grey means that this check has not yet been done. Red and dark red mean that the usage ratio for this check is greater than one, which means the check is not safe. Since the foundation is smaller than the face width of the tower, ASMTower has not performed any checks on the foundation yet. By changing the foundation dimension, these colours will change in the upper right corner of the dialog box. We will increase the dimension until we have all the indexes in yellow, green or blue. Set the length equal to 7 meters. Set the width equal to 7 meters. Now the columns are inside the foundation. Look at the upper right side of the dialog box. You can see that the overturning index is dark red. This means that it is extremely unsafe with a usage ratio of more than 1.4. Any check with a utilization ratio greater than 1 is unsafe and will be coloured in red or dark red. To make the foundation design more easily, ASMTower changes some design indexes each time you change the foundation input. There are 9 design indexes, 6 of which are updated each time you change the input. The remaining 3 indexes will not be coloured until you click the Design button and ASMTower successes in finite element analysis. The 3 indexes are the stress from the finite element analysis, the bottom reinforcement and the top reinforcement. The depth of groundwater is the depth of water within the soil measured from the surface of the earth. If it is 0, it means that the site is completely submerged and that the water is on the surface of the earth. If it equals a value greater than the depth of the foundation, the design will not be affected by the groundwater table. Now the depth value of the groundwater is cleared for that, the ASMTower treats it as equal to 0. Look at the upper right. You see that both the overturning and approximate pressure indexes are dark red. Set the depth of groundwater is equal to 5 meters. Look at the top right. You see that the overturning index colour becomes yellow. This is because the depth of groundwater was 0, which added a floating load to the foundation, and when we removed the presence of groundwater, the overturning became safe. Select the Master Foundation option. This will not affect any calculations, but will allow ASMTower to show the current foundation in the 3D drawing. only one foundation can be selected as a master foundation. So far, the foundation dimension is not enough because the approximate pressure on the soil is not safe. In order to make the overturning check or stress on the soil safe, you can increase the dimensions or depth of the foundations. These two factors are the most effective parameters you may use to enhance overturning safely or to reduce stress on the soil. Look at the colors of the approximate stress index as the foundation dimension increases. Set the length equal to 8 meters. Set the width equal to 8 meters. Now the approximate stress is not safe in red instead of dark red. Punching becomes safe in blue instead of red. This is because all the columns are located in the corner and we have increased the perimeter of the punching. The ASMTower automatically detects whether the column should be considered as a corner, edge, or intermediate column in the punching calculations. Increase the dimensions of the foundations again because the approximate stress is still not safe. The stress is now safe with green colors, which means the usage ratio is less than 0.85. Yellow color is our target, because it means safe and economic design. Try reducing the dimensions to 8.5 meters. Still green. Decrease the width to 8 meters and increase the depth of the foundation to 2.2 meters. Good, the stress index is now yellow. Increased foundation depth increased soil weight over foundation and increased contact area between foundation and soil. Thus, the stress on the soil decreased. In some special cases, you may need to design a foundation where the center of the tower is away from the center of the foundation. Eccentricity can be added to the X direction, the Z direction, or both directions. Adding eccentricity will increase the stress on the soil. In soil stress calculations, ASMTower automatically calculates soil stress, taking into account the effects of tower eccentricities. If we increase the eccentricity again, the punching check becomes unsafe because the columns on the right side have limited punching perimeters. Set the eccentric equal to 0. You see that the reinforcement rebar indexes are grey because we have not entered the rebar data and we have not analysed yet. Select the Pad Reinforcement tab. Assume the initial dimensions of the rebar and their suitability will be reviewed shortly. Enter the diameter of the bottom reinforcement bars equal to 16 millimeters. Enter the spacing between the lower reinforcement bars equals 150 millimeters. The bottom clear cover is equal to 75 millimeters. Enter the diameter of the upper reinforcement bars equal to 16 millimeters. Enter the spacing between the upper reinforcement bars equals to 200 millimeters. Enter the clear top cover equals 75 millimeters. Select the Column Reinforcement tab. Regarding the vertical reinforcement in the foundation column, set the diameter equal to 20 millimeters. Look at the top right. You see the vertical reinforcement index is still grey, which means not yet checked. Set the number of bars to equal 20. Look at the top right. You see the vertical reinforcement index becomes blue. This means that the amount of reinforcing bars is too high. Reduce the number of reinforcing bars to 16, but the design index is still green. Take the yellow color as the target because it means optimum design. Reduce it to 12. Fantastic! It turned yellow. Try the number equal to 8. The color becomes red, which means it is not safe. Set to 12. Suppose the diameter of the stirrup reinforcement bars is 10 millimeters. Spacing is equal to 200 millimeters. The stirrup reinforcement check index is blue, which means it is safe with usage ratio less than 0.6. But we will not try to decrease as we have already assumed low reinforcement. Set a clear side cover for stirrups equal to 50 mm. The remaining 3 indexes are still grey and will not be changed before you click the Design button. Click the Design button. Nothing happened. This is because clicking the Design button will perform the analysis to the foundation selected in the left list, and the left list is still empty. We must click the Add button first. Click the Add button. Click OK. You see that the foundation name is added to this list. Click the Design button. The ASMTower builds a finite element model for the mat foundation and solves iteratively under all wind directions and load combinations. You see the number of iterations needed for each load combination. ASMTower uses an iterative solver because the contact between the foundation and the soil is a non-linear problem that cannot be solved directly without iterations. Analysis is complete. Click Done. The report is saved in the same path where we saved the tower file. The report opens automatically after ASMTower saves it to disk. The cover page is on the first page. A summary of the design on the second page. The foundations are unsafe and coloured in red, showing that the usage ratio is 1.05 for verifying soil stress. Note that the ASMTower calculates 2 stress values on the soil. The first stress is calculated using approximate methods that assume a rigid foundation. This value does not appear in the report when the finite element analysis is succeeded. It only appears in the dialog box using the stress approximate index. The second stress is the exact stress that is calculated using the finite element analysis. Finite element analysis can handle flexible or rigid foundations. In this example, the first pressure assuming the rigidity of the foundations is greater than the second stress resulting from finite element analysis. Stress index color of finite element is red. That means unsafe. Try to increase the dimensions of the foundations to 8.1 meters. Click Update. Click Design. Analysis is complete. The foundation becomes safe. Click Done. Let's look at the report. This is a figure that shows a plan and elevation of the foundations with some dimensions. These are the foundation entries that we added in the dialog box. Detailed calculations for overturning stability. Detailed calculations for sliding stability. Detailed calculations to check the stress on the soil. Design bearing capacity against stress from factored loads. Maximum bearing stress on the soil due to factored loads. This is a detailed punch check calculation. It includes the calculation of the moment transferred from the columns to the mat foundation by eccentricity of the shear. ASMTower automatically detects whether the column will be considered a corner, edge or intermediate column in the punching calculations. Detailed calculations to check the bottom reinforcement. Applied bending moment versus bending moment strength. Detailed calculations for upper reinforcement. Detailed calculations of the minimum required reinforcement. Usage ratio of longitudinal rebars use in columns. This usage ratio is obtained from the interactive equation of the column that resists actual tension and bending moment. The bending moment is calculated due to the transfer of the shear force from the level of the tower leg to the level of the foundation surface. Verify that the minimum reinforcement in the column is met the design code requirements. Detailed calculations to the stirrup reinforcement bar in the column. This is the total foundation loads from the tower. We will see some figures resulting from finite element analysis. Maximum base pressure is found from the diagonal wind condition. Wind direction is 315 degrees and the name of the load combination is 0.9 times dead load plus 1.6 times wind load. The wind direction is in this direction. Maximum stress here in red. There is no contact between the foundation and the soil in the purple-coloured area. Suppose there are imaginary lines between different stress categories. These lines are not straight lines, but rather curved lines. In approximate stress calculation methods that assume the rigidity of the foundations, these lines are straight. The smaller the thickness of the foundations, the more curvature of these lines due to the flexibility of the foundations. This figure shows the summation of moment My plus absolute the moment Mxy for the critical combination that controlled the design of the bottom reinforcement. Similar figure to the top reinforcement. The last one was for the bottom. This figure shows My for the critical combination that controls the design. This figure shows Mxy for the critical combination that controls the design. Close the report. Click Update to refresh the graphic. The foundations appear in the 3D drawing because we set it as the master foundation. Now we will draw the foundation's details. From the Foundation Group, Lattice Tower Group, open the Matte dialog box. ASMTower asks to reanalyze the tower to update the reaction table in the foundation. Click Cancel. Click the Drawing button to provide the CAD file for the foundation that is selected in the left list. ASMTower asks to update the selected foundation with existing entries. Click the Update button if you want to update the selected foundation with the current entries. Click OK. Enter a name for the CAD file. Foundation Drawing. Click Save. Now your saved CAD file will open automatically by your default CAD software. Now the CAD file opens. The drawing includes a plan for the foundation in the lower left side of the drawing. A cross-section in the foundation in the upper left. Table to the reinforcement bar schedule in the upper right side. This is the plan. The upper and lower reinforcement are marked in each direction. For example, the bottom reinforcement is marked by 16-1-150-B1. 16 means reinforcement with a diameter equal to 16 mm. 1 is the reinforcement mark number. The same mark number is used in the reinforcement schedule table. 150 is the spacing between the reinforcing bars in millimeters. B1 means lower reinforcement in direction 1. T2 means upper reinforcement in direction 2. Direction 1 is the direction of the horizontal axis in the drawing, while direction 2 is the direction of the vertical axis in the drawing. Now you see a cross-section in the foundations showing the rebar. Each rebar is marked by a number. This is the table of the reinforcement bar's schedule. For each bar, the table displays the bar diameter, quantity, length, and detailed shape. On the right side, notes were added showing the design criteria. This is the total weight of all reinforcing bars and is equal to 29.36 kN. The volume of reinforced concrete is equal to 34.8 cubic meters. This volume includes the volume of the concrete pad and the volume of the 4 columns.